Hey, sorry I'm not there today. This is the pre-lab for Tuesday and Wednesday's lab, the making of and detonating of nitrogen triiodide. And this video is going to explore the energy considerations involved in the explosion. But before we get specifically to that, I want to talk about two issues. The two driving forces of nature. The first is that nature has a tendency toward a decrease in potential energy, and that's something that we've talked a little bit about here and there. But something else that's very important that we haven't talked about is nature's tendency toward an increase in entropy. And that plays a large part in what we're doing here today. We're doing two reactions. One is making the explosive, that's one chemical reaction, and then the other is the detonation, the explosion itself. So we're not going to talk much about entropy now. We're going to talk more about it while we're waiting for the nitrogen triiodide to dry out. But just briefly, entropy has really three definitions that are all very related to each other. One is an increase in system disorder, another a greater spread of energy in the system, and the third is a decrease in availability of information about the system. These are all really just different perspectives on the same thing. And I'm really not going to go much into it other than to just throw out a challenge if anybody's interested in taking up the challenge, which is, given that this is the first reaction we're doing, the synthesis of Ni3, the explosive, can you think of any reason why entropy might be increasing or decreasing in the products versus the reactants? So the question is, if you would care to explore it, do the products have more entropy or less entropy given the definitions that I've given you here on the screen? And we'll definitely talk about it in class, but something for you to think about and chew on. Okay, so let's move on to the energy part of this process. First of all, we need to understand that in the synthesis of nitrogen triiodide, the iodines are so large compared to the nitrogen that they don't really quite fit around the nitrogen. And in fact, there's a great deal of repulsion between the iodines. And this kind of repulsion is very important in chemistry. It happens all the time, the repulsion between atoms in a molecule. And here the repulsion is quite large because the iodines are so close to each other. And it has a name called steric strain or steric hindrance. These are common terms for that kind of large repulsion. And so what this tells us is that Ni3 is not a very stable molecule. It's those iodines don't want to be there. So that tells us why Ni3 so easily falls apart, so easily decomposes. But it doesn't actually tell us why it explodes. If we want to know why it explodes, we have to understand the energy considerations. So let's take a look at that. First, we really have to get into an understanding of what potential energy is. So in the world of physics, you would think of a rock sitting on the ground at this starting point having zero potential energy. And if you lift it up, you would increase its potential energy as it gets further from the Earth. And so we can look at this as potential energy as being the result of distance from the Earth. The greater the distance, the larger the potential energy. In other words, it has the potential to do work as you let go of it, and potential energy decreases. However, yes, even in physics, believe it or not, there is something called conservation of energy. So a better way of looking at this is to look and see how energy is conserved. As the rock gets closer to the Earth and decreases in potential energy, it has in exact proportion an increase in kinetic energy. Now you would think that the kinetic energy has now gone to zero at this point, but of course it has not. The kinetic energy is just transferred to the Earth. We have saved the law of conservation of energy. So how do we relate this to what's going on in a chemical process? Let's take a look. For the decomposition of Ni3, what we get is one nitrogen molecule and 3 iodine molecules. And these are gases. I guess I should have written that. But to really understand why an explosion occurs as opposed to just a decomposition, we have to look at nitrogen in particular. So nitrogen is triple bonded, and that triple bond has an incredibly high bond energy, 941 kilojoules per mole. So you'd have to add 941 kilojoules in order to break a mole of those bonds. That's a very large amount of energy. That's a very high bond energy. And what that tells us is that nitrogen is an incredibly stable, low potential energy molecule. It has an incredibly long half-life in the atmosphere. Most of that half-life is simply due to lightning. When lightning comes around, it will split the N2 molecule. So it takes a lot of energy, and normally in the atmosphere, there's not enough energy for nitrogen to break apart. And so it has an extremely long half-life, very stable molecule. Okay, that's a very important consideration. Let's move on. Yes, very low potential energy. So if we look at the difference in potential energy, Ni3 has a very high potential energy. And we need to have a little bit better of a definition for potential energy in chemistry, even though in chemistry it is still the energy of position, just like in physics, except here it's the position of the electrons. The electrons in a lower potential energy molecule actually have a closer average distance from the nucleus than in higher potential energy molecules. However, a more practical way of thinking about it is, just like in physics, we can think of potential energy as the potential to do work. In chemistry, we think of potential energy as the potential to undergo a chemical reaction. So Ni3 has a very high potential to undergo a chemical reaction. Molecular nitrogen, N2, has an extremely low potential to undergo a chemical reaction. If we just look at the difference between the Ni3 molecule and the N2 molecule, we see that there's a very large difference in potential energy. But we need to obey the law of conservation of energy. And so what does that mean for kinetic energy? Well, the kinetic energy is going to increase dramatically in the nitrogen. What that means is, as potential energy decreases, N2 kinetic energy dramatically increases. Of course, we're not dealing with a single nitrogen molecule. We're dealing with quintillions of nitrogen molecules. And that very high kinetic energy nitrogen is the explosion. There's a sudden formation of quadrillions of high-speed nitrogen molecules that are shooting out from the reaction and creating a pressure wave as they bump into and transfer that energy into the air molecules. And that pressure wave reaches your ears and you hear a loud pop. And that's only because we're using a very, very tiny amount. If we use a large amount, you would hear a very big pop, and you might even feel it enough in your body. And if we used an even larger amount, it would push your body completely over, just like you see in the movies. That's actually real. That's how explosions destroy things. It's just the energy of the gases, the high-speed gases that are pushing things apart. But what's really interesting about this particular reaction, this explosion, is what happens with the iodine. So the iodine has a much higher potential energy than nitrogen, and so the difference in potential energy between Ni3 and iodine is not very much. And so when the iodine forms, its kinetic energy is not very much, and so it just sort of comes out of the reaction as a growing cloud of purple smoke. So there's a much smaller change in the potential energy of the iodine, meaning that the amount of kinetic energy the iodine has is much less. This is not going to cause an explosion, these slow-moving gas molecules. You need the high-speed gas molecules that the N2 provides to cause the explosion. And of course, we're talking about quadrillions and quintillions of particles. The end. See ya.